Hello, everyone, and welcome to today's webinar, which is brought to you by Bettersize Instruments in partnership with AZO Network. Today's webinar is titled Revving Up Solid State Batteries Particle Analysis for Peak Performance. A big thank you to the team at Bettersize Instruments for making this event possible. We're going to get started in a couple of minutes, but before we do, let me introduce today's wonderful speakers and explain a little bit about the format for today's webinar. Today's webinar will run as two parts, two presentations and an audience Q&A session. The first of today's fantastic speakers, who will get us started in just a moment, is Beverly Barnum, Senior Application Scientist at Bettersize Inc. She received her BS in chemistry from California State University and her PhD in inorganic chemistry from the University of Pennsylvania. Renowned for her analytical expertise and innovative problem solving, Dr. Barnum brings deep insight into particle characterization technologies. Beverly is joined by Weichen, an application scientist at Bettersize Instruments, specializing in the characterization of physical properties of inorganic materials. With degrees in material science from the Harbin Institute of Technology and the University of Florida, he assists global researchers in optimizing materials using Bettersize analytical solutions. A big welcome to you both today. Before getting started, we have a few points about how to get the most out of your experience today. Firstly, the event is being recorded and we will share the on-demand link with you within the next 24 hours. So, if you enjoy what you see, or you have a colleague or peer who may benefit from seeing the content as well, please do share that recording with them when you get that email. Refreshing your browser normally resolves technical issues. But if this doesn't work, send a message using the Q&A box and our backend team will get you back up and running as soon as possible. As I mentioned, there will be a Q&A session following the presentation, so please send those questions in at any time and we'll get to as many of them as possible following the presentation. A quick note that if you are watching this webinar back on demand, then you can still ask your questions, but you will receive an answer via email. Now, let's get things started with the presentation. Beverly, over to you.
Thank you for that kind introduction. Hello, everyone. Today, we'll explore why particle size analysis is critical in solid-state battery development and how it impacts performance. Solid-state batteries, or SSBs, as I'm going to refer to them, are widely regarded as the next finish line in energy storage, offering higher energy density, improved safety, and faster charging times when compared to conventional lithium-ion batteries. In terms of market context, consumer electronic companies are exploring SSBs for smartphones, laptops, and wearables because they enable slimmer designs and longer battery life, safer operation, and reduce the risk of overheating. For anyone who's ever left their iPhone on the dash of their car, you know what I'm talking about. SSBs are also being considered for grid scale energy storage to support and stabilize renewable energy sources like wind and solar power. The advantages include longer lifespan, and they're safer when compared again to lithium-ion storage. Aerospace applications include electric aircraft and drones, which require lightweight, high-performance batteries. Industrial machinery and medical equipment companies are looking at the benefits from the high reliability and safety and long operational life and reduced maintenance. And this is particularly useful in environments where downtime is costly and safety is critical. But by and large, the global electric vehicle market is driving the demand for safer, high-performance batteries. Analysts predict that SSB adoption will grow exponentially by 2030. In fact, Stellantis and GAC will be releasing pilot vehicles in 2026, with Toyota and SAIC releasing mass vehicles launching in 2027. Nissan and other EV manufacturers worldwide are not far behind in the adoption of SSBs. So I would say, drivers, start your engine. But now, with SSBs, I'll say, drivers, unplug your vehicles and let's hit the road. So again, solid-state batteries promise to revolutionize energy storage, but the real breakthrough lies in mastering particle-level control. Why? Because microstructural precision determines the conductivity, the safety, and durability of SSBs. The objective of today's talk is to show how particle-level analysis, specifically particle size, morphology, and density analysis, directly influence energy efficiency, safety, and life cycle, and why this data accelerates innovation and enhances performance, which is critical for scaling solid-state battery technology. Looking at this diagram, we can see the key components of the solid-state battery, SSB. Basically, it stores and releases lithium ions to the electrodes. On the right, we have the anode. And this is the electrode where oxidation reactions occur during discharge. Anode materials in solid-state batteries often include metallic lithium, lithium titanate, or silicon-based materials. In the middle of the SSB, we have the solid electrolyte. Solid electrolytes are typically made of solid materials. These conduct ions between the cathode and the anode. And examples include solid-state ceramic separators like lithium phosphorus oxynitride, sulfides like lithium sulfide, or polymers like polyethylene oxide complex with salts. And on the left, we have the cathode. This is the electrode where reduction reactions occur during discharge. The positive electrode, the cathode, is typically a lithium-based metal oxide or phosphate with an aluminum current collector. The cathode, active materials, CAM. Common materials include LCO, LFP, NMC, LCA, NCA. So if we look at the differences between traditional lithium-ion batteries and solid-state batteries, the key component is the electrolyte difference. Solid-state batteries using the solid electrolytes, such as sulfides and oxides, perform better in terms of stability, safety, and thermal conductivity, and these do not leak or evaporate. There's also differences in the electrode material selection. The anodes in solid-state batteries often include metallic lithium, lithium titanate, or silicon-based materials. And this allows for the increased energy density of solid-state batteries. The biggest difference with these electrolyte and electrode materials is that there is in the interface characteristics. Because we are going from solid-liquid contact to solid-solid contact, this results in smaller contact area, and we have higher interface resistance. So while SSBs have a negative cost difference, the gains are energy density, charging speed, and thermal stability. So let's look at a little bit of the pros and cons of these. So for the pros, we have, again, enhanced safety. Again, we don't have a flammable liquid electrolyte, and so we reduce the risk of fires and explosions. We have longer lifespans. We have faster charging. We have higher energy density. The solid-state batteries provide higher energy density, and this allows us to have smaller devices and longer battery life. But we have the issues of interface resistance, material compatibility, and production scalability, as this is newer technology. And these are major challenges in solid-state battery development. In terms of the manufacturing, we have high manufacturing costs as we are developing new technology and scaling up, and material compatibility issues. If we look at the current technology challenges, this involves, again, optimizing electrolyte compositions, developing new solid electrolyte materials with enhanced stability and conductivity. Key performance drivers will continue to be the energy density, the ionic conductivity, and thermal stability, which is critical to enhance the solid-state battery performance. So let's look at the influence of particle properties. Particle size and density affect the packing density of the materials, the conductivity, and the mechanical strength of solid-state batteries. So why does particle size matter so much? Because the interfaces between the particles and the electrolyte are key for ion transport. So the particles, if we look at this solid-state battery, particles and powders influence electrode packing and the interface contact in the architecture of the solid-state battery. By controlling particle properties, we can ensure uniformity and stability, which is vital for peak battery performance. The particle characteristics directly affect the overall electrical conductivity of solid-state batteries. In SSB architecture, the powders and microstructures are essential for creating these effective ion transport pathways and maintaining mechanical integrity. The physical properties of the powdered materials, their size, their shape, and their composition, and the resulting internal structure of the battery components, the electrodes and the electrolytes, directly determine performance, safety, and lifespan. The emphasis here is on three main roles: the ionic conductivity, where smaller particles can increase contact area and improve ion flow; packing density, where optimized size reduces voids, and this increases our energy density; and the mechanical stability. Having uniform size will prevent cracking during cycling. So let's look at the basics of particle size and analysis. Particle size, again, affects the packing density. It is the surface area and the reaction kinetics of materials in these applications. The key parameters include the D50, which is the median particle size, meaning it represents the particle diameter, which 50% of the sample's particles are smaller and 50% are larger. So this is the key parameter for describing the particle size distribution. So what's a particle size distribution? PSD refers to the statistical distribution of particle sizes in a sample and is typically represented by a histogram or a cumulative distribution curve. And this provides information about the range of particle sizes present, the ratio of the particles within each size range, and the distribution pattern of particle sizes across the sample. PSD is crucial in battery manufacturing due to its direct impact on the performance, efficiency, and safety of the batteries. How do we measure particle size? There's common techniques include sieving, imaging, sedimentation, laser diffraction, dynamic light scattering, photoresist, X-ray scattering, and there's pros and cons to all of these. I'll highlight a few right here and talk about sieving, which is a traditional method for separating granular materials into different size fractions by using a series of sieves with decreasing mesh or hole sizes. This is very simple and very inexpensive to do, but is very imprecise. Laser diffraction is a common technique that measures particle size by analyzing light scattering patterns. And this measures larger particles in the range from 10 nanometers to 3.5 millimeters. Dynamic light scattering analyzes particles by measuring fluctuations in scattered light to determine size. And this is best for particles in the nanometer size range. Microscopy allows for direct visualization and measurement of particle size and morphology in samples from less than a micron up to 25 millimeters. However, no single technique gives the full picture, and often a combination is used. So if we look specifically at the particle size, this refers to the diameter of the individual particle. It's not just about average size. The distribution matters. So the metrics like the D10, the D50, and the D90 tell us how uniform the powder is. Narrow distribution means better packing and predictable performance. Wide distributions could lead to uneven interfaces and inconsistent conductivity. So again, when we look at the D50, which is the mean particle size, this will help determine the key battery properties influencing performance. Here you just see an image of an SEM, two different grain sizes. So let's look at the impact of particle size on performance. Smaller particles generally improve contact and reduce interfacial resistance, which boosts ionic conductivity. They also sinter more easily and create dense microstructures. But there's a trade-off. Too fine a particle can agglomerate, and this can cause uneven packing and contamination risks. Overall, the smaller particles improve ionic conductivity, but may increase surface reactivity and instabilities. Larger particles can contribute to the enhanced mechanical stability. However, it's at the cost of conductivity. So optimizing battery performance requires balancing particle size to maximize conductivity and stability. Density is another critical parameter. True density is the mass of a material divided by the volume of the solid material itself. excluding all pores, voids, and cracks. This is also known as absolute density, and it represents the intrinsic density of the solid particles and is a fundamental material property. This can be measured by gas picnometry. This is different from bulk density, which includes the volume of empty spaces between the particles, as you can see, the closed pores and whatnot. This tap density can reflect how powders pack under vibration, which is key for manufacturing. And a higher tap density means there's fewer voids and better volumetric energy density. Low density leads to higher porosity, which can compromise performance. So bulk density defined is the mass of the particles per unit volume without implying compaction. And the tap density measures the particle mass per unit volume after compaction by tapping. So the particle densities influence electrode uniformity and overall energy storage capacity. High-density powders improve structural integrity and reduce voids, which enhances ionic conductivity. Low-density powders create porous structures that crack under cycling stress, and lower energy density. This is why the density control is as important as particle size optimization. The application of tap density is an important indicator of how well the active materials are packed in a battery, and this directly affects energy density and endurance. High tap density means more active material can fit in the same volume, thus enhancing the battery's density. Particle size determines how well powders pack and center, while density impacts porosity and volumetric energy. Both of these are essential for creating efficient ionic pathways and strong interfaces. Size and density are interdependent. Again, fine densities can improve packing, but may lower tap density if they agglomerate. The goal is to balance both for minimal porosity, maximum contact. This interplay determines the conductivity, mechanical stability, and ultimate cycle life. So when we combine the analysis of particle size and density, we reveal effects on conductivity and interface integrity. Using combined data will ensure optimized material design for enhanced cycle life and peak performance. These techniques can give us critical insights. In this image here, you can see laser diffraction provides size distribution, and the microscopy reveals the morphology, and picnometry can measure true density. Together, they can help predict performance. Uniform particle size and high density, again, reduces voids, improves conductivity, and mechanical strength. These are the goals. This translates into the higher energy density and better cycle life. Volumetric and gravimetric methods for density measurements are used to determine particle density effectively. Particle size analysis through laser diffraction and microscopy can measure particle size and shape to accurately analyze the material. These outputs are generally size distribution curves, mean particle size, and density values. Again, from a manufacturing and quality control point of view, we stress consistency. Uniform particle size is critical for reproducibility. However, the challenge is maintaining tight control at an industrial scale. So particle size and density, again, determine the quality of the interface contact between battery materials, and this affects the performance. The optimized particle properties can create efficient ionic pathways, which reduce resistance and improve conductivity. And proper density control can ensure mechanical integrity, enhancing cycle life and battery durability. Here's a study on an anode material, which is graphite. The D50 obtained from the particle size measurements versus its tap density are presented in the figure. The tap density increases with the increase of the medium particle size, or the D50. The larger particles achieve higher tap densities by more effectively filling the voids between the particle, reducing the interparticle space compared to smaller particles. A higher tap density is beneficial for enhancing the battery's energy density. However, this increase is accompanied by a rise in particle size, which may lead to negative consequences, So you have to balance, again, the pros and the cons. Again, all this has to do with the interfaces. The interfaces are critical. Poor particle control will lead to uneven contact, stress points, and cracks, and this will shorten the cycle life. By improving the particle properties, we enhance the stability of the battery interfaces, reducing the degradation over time. So we're looking at here the interface between the anode and the solid-state electrolyte, the interfaces within the solid-state electrolytes, and the interface between the solid-state electrolyte and the cathode active material. By achieving stable interfaces through particle optimization, we can extend the battery's operational cycle and life safety. Optimizing the particles contributes to the battery with a higher energy density and improved efficiency. And particle analysis is fundamental for advancing solid-state technology and improving performance. This is a very complicated image on purpose, and this shows the current material challenges for solid-state batteries. These revolve around achieving high performance, stability, and manufacturability. There are major issues, including the limits of solid electrolytes, which have low ionic conductivity at room temperature versus liquid electrolytes. There's grain boundary resistance in ceramic electrolytes, which reduce the overall performance. There's moisture sensitivity, especially for sulfide-based electrolytes, which make handling and processing difficult. Another key limitation is the interface instability. Again, poor contact between electrolyte and electrodes can result due to the rigid materials that are being used. Chemical reactions at interfaces can lead to increased resistance and degradation. Lithium dendrite penetration through solid electrolytes can cause short circuits. We have, again, the mechanical challenges. The brittleness of ceramic electrolytes can make them are prone to cracking under stress. We have volume changes during cycling, especially with lithium metal anodes, which cause a loss of contact and mechanical failure. Material compatibility. We often have mismatches between the electrodes and the electrolyte, and this can occur with cathodes, can often react with the sulfide or oxide electrolytes, and lithium metal can form unstable interfaces with many solid electrolytes. In terms of manufacturing and scalability, high process temperatures for electrolyte made of oxides will increase the cost and the complexity of manufacturing. There's difficulty in achieving thin, defect-free layers for high energy density. Quality control can be improved by measuring particle size and uniformity on the industrial scale, however. In terms of cost and resource constraints, obviously we have to deal with the expensive raw materials for some of the high-performance electrolytes and complex fabrication processes, which limit the commercial viability of scaling up. Key optimization strategies for solid-state battery development include material selection and interface engineering, and particle size and morphology control. By tailoring the particle size distribution, we can improve packing density and ionic pathways. By surface modification, using coatings or dopants to enhance compatibility, we can reduce side reactions. And there's new research into nanostructuring, where smaller particles for better kinetics can be balanced with stability concerns. So now there is development, in fact, using electrolytes that have layered structures with smaller particles and larger particles, literally layered in that solid state electrolyte. In terms of manufacturing of manufacturing scalability, we have quality control, where we need to monitor particle size and thickness for consistency, and improvements in system level design. So that was a whole lot in not a lot of time, but I wanted to let you know some key takeaways. So obviously the importance of particle size in solid state batteries. This again is related to the big three: ionic conductivity, packing density, and mechanical stability, and how this impacts the electrochemical performance, which is related to the charge and discharge rates, the cycle life, and the safety of the solid state battery. And remind you of the different techniques for particle size analysis and particle analysis, which is laser diffraction, tap density, and gas picnometry, which are related to density. There are optimization strategies, but they do involve trade-offs between large and small, and uniformity, and also there's development in tailored distributions. Again, where I was talking about the layering of different size materials in the solid state electrodes. And the effects on manufacturing. So particle analysis helps assure consistency and quality assurance. And very quickly, I want to thank you for paying attention to the first half of this presentation. And now I'll pass this over in part 2 to my colleague, Weichen, who's going to have more details on how to perform these characterizations with some interesting real-world examples. Thanks for your time.
Thank you, Beverly, for walking us through why physical characteristics are so critical for solid-state battery performance. Hello, everyone. My name is Weichen, an application scientist at Bettersize, Inc. In this next section, we will shift our focus to the how, specifically the practical methods for measuring particle size as well as tap and chew density for these sensitive materials. We have organized this practical section into 3 key sections. First, we will tackle challenges of measuring SSE particle size, specifically focusing on handling reactive sulfide materials. Then, we will move on to tap density to understand material processability. And finally, we will discuss chew density measurements to ensure material quality and phase purity. To measure these particles accurately, we rely on laser diffraction and mean scattering theory. The core rule is simple. Large particles scatter light at narrow angles, creating tight, intense rings, while small particles scatter light at wide angles, creating broader, diffuse patterns. By capturing these diffraction rings, like the ones you see on the right, our detectors can mathematically construct the exact size of every particle in your mixture. So, how do we turn that ring pattern into a graph? First, the detector captures the raw scattering spectrum, which is essentially a composite signal of light scattered by every particle in the chamber. To decode this, we apply mean theory, which acts as a reference library to identify which specific ring pattern corresponds to which particle size. Next, the algorithm solves the equation to determine that we need A% of one pattern and B% of another, etc., etc., to perfectly recreate the measured signal. Finally, these calculated percentages are plotted to generate the precise particle size distribution curve you see here. Now we understand the theory. The practical challenge becomes dispersion. How to separate sticky particles to measure them individually. We have 2 main passes. Wet dispersion on the left uses solvents and ultrasound. It is the gold standard for R&D because it breaks up through agglomerates for maximum accuracy. Dry dispersion on the right uses compressed gas. It offers the speed and repeatability needed for high volume quality control. Now, let's talk about the Bettersize 2600 laser diffraction particle size analyzer itself. Its tagline, "Better particle sizing for every need," really sums it up. This award-winning instrument, recognized with the 2024 iNovo Award, offers unparalleled measurement capabilities with its modular design, from slurries to raw materials as dry powders. With its unique optical design, the Bettersize 2600 boasts an exceptionally wide particle size range, handling everything from 0.02 to 2,600 microns with wet dispersion and 0.1 to 2600 microns with dry dispersion. Beyond size, the Bettersize 2600 also measures particle shape, another crucial factor thanks to the powerful P1 image analysis module. For even larger particles, its dynamic imaging capability covers 2 to 3,500 microns. This versatility is achieved through its unique combination of laser diffraction for rapid size analysis and dynamic imaging for detailed shape information. As we just discussed, the beauty of the Bettersize 2600 is its modular design. It allows you to switch between wet and dry dispersion units on the same instrument. To apply this versatility to sulfide solid-state electrolyte materials, we integrate this entire system into a glove box. This gives you the flexibility to run wet dispersion with solvents or run dry dispersion with inert gas without even exposing your sample to the air. Let's look at a real-world setup for quality control of sulfide powders. Here, the dry dispersion module is installed inside a nitrogen-filled glove box with a Teflon-coated chute to ensure sticky powders flow smoothly. You will also notice the vacuum cleaner integrated directly inside the box also. This captures the dispersed powder immediately after measurement, allowing for sample recollection and preventing the glove box filters from getting clogged. And during the whole process, no powders was exposed to any moisture or oxygen. Now, let's look at the wet dispersion setup, which is critical for monitoring the grinding process of sulfide slurries. We use the BT-ATN small volume units here. This is a strategic choice because it drastically reduces the composition of expensive anhydrous and heptane. Notice the disposal bucket integrated directly into the workspace. This is crucial for safely draining the hazardous solvent waste immediately after testing, without ever breaking the inert nitrogen atmosphere. Having mastered how to measure the size of individual particles, we now move on to the collective behavior of the powder. In this next section, we will focus on bulk and tap density. As we have covered in the earlier part, these metrics are the key to understanding flowability and compressibility, the factors that determine how easily you can process these powders into uniform and high-density electrode layers. To capture these critical parameters efficiently, we use the Powder Pro A1. This is a fully automated 14-in-1 workstation that replaces traditional manual testing methods, completely eliminating human error. By physically measuring properties like tap density and angle of repose, it also automatically calculates the Carr index, giving you an instant, comprehensive profile of your material's flowability and floatability in a single test run. For labs that specifically require high-throughput density testing compliant with USP and ASTM standards, we offer the BeDensi T Pro Series. This dedicated system can run up to 3 samples simultaneously, tripling your testing speed compared to single-station units. It is designed for simplicity and precision, delivering bulk and tap density results with less than 1% variation, ensuring your data is consistent, reliable, and audit-ready. Let's look at a practical case study involving LFP cathode materials. We know that high tap density is critical for maximizing volumetric energy density. However, this data reveals a critical insight. Finer particles do not always pack better. Comparing these two samples, the LFP1, the blue curve was overground to a fine 4 microns, yet it resulted in a lower density of 0.89 grams per cubic meter centimeter. Meanwhile, the optimized LFP2, the green curve with a larger size of 9 microns, achieved a significantly higher density of 1.08 grams per cubic centimeter. By using the BeDensi T Pro, we were able to clearly identify this sweet spot in production with the ASTM compliant precision and less than 1% variation. We have explored how particle size affects packing and how bulk density predicts processability. Now, we turn to the final piece of the puzzle, true density. This metric measures the density of the solid material itself, excluding all open pores and voids, giving us the absolute baseline required for verifying phase purity and calculating precise electrode coating recipes. To measure the volume of irregular powders in batteries, we can't use a ruler, so we use gas, typically helium or nitrogen. The process is clever and is governed by a classic physics principle called Boyle's law, which relates pressure and volume. Simply put, Boyle's law states that if you squeeze a gas into a small volume, its pressure increases. If you let it expand into a larger volume, its pressure decreases. A pygnometer uses this exact principle into two simple stages. First, the instrument needs a baseline. Put the weighted sample inside the sample chamber and then fills the sample chamber with inert gas, like helium, to a set pressure P1. Then, the expansion valve to a second chamber opens, allowing the gas to expand. The transducer will precisely measure a new, lower pressure P2. As the equation shows, the volume of sample V can be calculated both based on the sample chamber volume VSC, two pressure values P1 and P2, and the reference chamber volume VRC. The VSC, VRC, and P1 are previously input into the software as the pressure transducer reaches out P2 accurately. The sample volume can be calculated with incredible precision. Once the volume is known, the instrument simply takes the previously entered mass and calculates the true density, mass divided by volume. Now that we understand the gas displacement method, let's meet the instrument that perfects it, the BetterPick 380. This is a versatile, multifunctional tool. It measures not only true density and volume, but also the solid content and open and closed cell content for materials like foams. It delivers high precise results thanks to the excellent temperature and pressure control, and it fully complies with the key ASTM and ISO standards, so you can be confident in your data. While it really simplifies your work is the automatic workflow. The intuitive software can connect directly to your lab balance to automatically import in the sample mass, making the entire process incredibly simple and efficient. In short, the Bettersize 380 is designed to be the ideal, easy-to-use pygnometer for both demanding research and fast-paced production environments. Here is the bottom line. the BetterPick 380 turns chew density into a rigorous quality control parameter. If you look at the data on the right, 5 consecutive runs on the cathode material yielded a relative standard deviation (RSD) of just 0.018%. This level of precision is impossible with the traditional messy Le Chatelier flask method. Furthermore, specifically for sulfide SSEs, this system allows us to measure volume without exposure to moisture or oxygen, ensuring the chemical integrity of your sample remains synonymous with your data integrity. Finally, you don't have to take our word for it. The solutions we discussed today are already actively deployed by major leaders in the solid-state battery revolution. For materials pioneers like Ganfeng Lithium to cutting-edge research institutes like Tianmu Lake, top-tier players rely on Bettersize instruments to optimize their electrode manufacturing. We are proud to power these success stories, and we look forward to help you write the next chapter in cleaner, smarter energy storage. To wrap up our section, let's recap the scientific principles and practical solutions we explored today. First, for particle size, we rely on laser diffraction and mirror theory for the highest resolution data. But for sulfides, the physics is useless without safety. That is why glove box integration with the Bettersize 2600 is essential. It ensures you measure the actual particle, not a hybridized degradation product. Second, for tap density, we focus on the link to volumetric energy density. We learned a critical lesson. Smaller does not always mean denser. You must monitor tap density to find the manufacturing sweet spot and avoid overgrinding your material. Finally, for chew density, we utilize the gas displacement method based on Boyle's law. This allows us to look past the air gaps and measure the solid material itself, giving you an absolute baseline needed for phase purity and coating consistency. At Bettersize, our goal is to combine these robust principles with safe, automated engineering to help you build the next generation of batteries. Thank you very much for your time and attention today. For more detailed application notes on this specific sulfide test, please visit our website listed on the screen. Dr. Beverly, Barnum, and I are now very happy to take any questions you may have. Thank you.
Hello, everyone. Dr. Beverly Barnum is joining me for the Q&A. You may notice that Weichen is not available. He has been disconnected, and we are working hard to get him reconnected. He may still have time to answer some questions, so please do send those in. If we don't get round to your questions or we can't get Weichen reconnected, then you will receive an answer via email. Likewise, if you're watching this webinar on demand, then still ask questions, but again, you will receive an answer via email. A reminder to download any handouts that we've got. They're available. Thank you to Beverly and Weichen for their presentations, and we'll go into the Q&A. So our first question, we've got a couple to get us started. We know smaller particles generally offer better contact. Why don't we just grind everything down to the smallest possible size?
Okay, so it's a trade-off. Now, of course, in terms of manufacturing, the longer you grind, the more time it takes and all the energy involved with that. And while smaller particles do offer lower interfacial resistance and improved sintering, they do introduce significant risks. as the smaller particles, the finer particles are more prone to agglomeration, which causes uneven packing in the end, and they have higher surface reactivity, which increases the risk of contamination. So again, it's a trade-off. So again, it would cost more, and it may not, making everything smaller doesn't make everything better. So.
Perfect, thank you. And why is tap density specifically emphasized over just regular density?
So while we can talk about like true density is the intrinsic material itself, but that material is made up of smaller particles, which is what we're measuring. A tap density indicates the actual packing behavior of the powder. And when we're dealing in manufacturing, even when we're dealing this with materials, when you have to move the sugar shaker or the salt shaker, that the tap density over time, it increases the density itself. So it's crucial that because high tap density leads to lower porosity. So the contact of the particles themselves are much more physically closer. And this is a better mechanical integrity of that will result in a better mechanical integrity with the final battery structure. Now, if we have lower density, increased porosity, and then this could lead to cracks during cycling. So this is why tap density is usually the key feature when we're talking about battery manufacturer.
Perfect, thank you. And staying on the topic of tap density and its use, is there an outer to inner gradation of particles, gravity, and heat that is important, that must be crucial?
So it's that question again. Okay, so in terms of tap density, where did my question go? Sorry. Okay, so the question sounded funny. I apologize. So in terms of when you're operating the tap density, um, typical tap density instruments operate between 10 and 35 or 45 C. And this is the ambient temperature range where the instrument works reliably. For our series of tap density or BeDensi instruments, it actually operates to 65 C. The whole point of tap density is we're packing it down, and again, it should be level. And again, due to all the van der Waals forces and all this, so we're going to get the small, and the whole point of tapping it is to get the smaller particles and to pack it as much as possible. You should not have a gradient in terms of temperature because it is, well, I'm sorry, it's recommended that you have to ensure that the powder is dry and it's at a stable temperature. So you're not adding cold powders into a small tap density instrument. So everything should be at the same temperature. And then at that point, it's not gravity. We're actually physically tapping it down. So we're adding energy to basically pack that material down into its densest packing form.
Thank you. And the next question is the slides mention sintering behavior. How does particle analysis help us predict that?
Right. So we got a few things going on here. Hold on, I'm going crazy. So let's talk about. All right. Oh, goodness gracious! I'm trying to read
So,
this.
yeah, we're on
Sorry.
sintering behavior.
Okay. So again, as I said before, the finer powders basically have this great more surface area, and so again, when we're talking about sintering, this is a thermal process. So basically, when we're in the production, we're talking about compacting the electrolyte powder to just below its melting point, so it's kind of mushy, we'll say, and this fuses the particles together, and so this will create a denser, solider, more solid and integrated material. And so that's the sintering process. And so in terms by measuring the doing measurements on the particle size, we can assure that this sintering is going to be effective. So we can predict how well it will behave during the heating process. If they're too coarse, of course, they won't sinter very densely because there'll be voids in there. If we have two big pieces, there'll be a gap in between. Whereas if we have uniform size, then generally we get good packing, and then we can have accomplish a good sintering of that material. And basically, we're densifying it.
Thank you. And with the wet dispersion unit inside the glove box, cleaning seems difficult. How do you handle the waste solvent?
Um, uh, so Weichen presented that in his part of it, and he did show that they basically had a containment bucket within the inert atmospheres box itself. So again, they used a smaller volume, the BT80N. So the 80 for that is 80 mils volume for that dispersion unit. So they have a dedicated drain tube, and that can go into a sealed waste container inside the box. So basically, you don't have to handle open buckets of waste in there, and it's within the inert atmospheres environment. And so then afterwards, you just close that up and take that out. So basically, we're minimizing any exposure of that material.
And the final question we've got time for today, for dry dispersion, can we use the glove box atmosphere itself, or do we need a separate gas line?
Oh, okay. So for the instrument itself, when we're doing the dry dispersion for laser diffraction, two things. Generally, when you do dry laser diffraction, you do a pressure titration, so you have to vary the pressure within it. And so this is a higher pressure requirement of varying between 1 up to even 5 bars of pressure in order to separate the agglomerates. Most glove boxes are just a few millibars above atmosphere, because when you're filling that up, you don't require a lot of pressure. So generally, we recommend that you have to have a separate, because you don't want to blow out the inert atmospheres box. Excuse me, I said dry box. So we recommend that you connect a separate nitrogen cylinder or inert gas cylinder, excuse me, to operate pressurized line required for laser diffraction to work the venturi pump to separate the agglomerates for laser diffraction. So you would need basically two tanks for that.
Perfect. Thank you, Beverly. Thank you for participating in our Q&A. If you do have any more questions for Beverly or for Weichen, then please do ask them. You will receive an answer by email. Before you leave us today, remember to download any handouts. Beverly, any final thoughts before we leave our audience today?
Oh, goodness gracious. I think I emphasized many times the big three, but again, feel free to reach out on our email line, because we're always happy to answer questions. And of course, this is a very compacted presentation, and we do deal with a large number of companies dealing with batteries. So we do appreciate your questions. Sometimes it's just very difficult to answer specific questions, a general question in a specific amount of time, but our research and development team are always happy to lend support. So please reach out to us.
Perfect. Thank you, Beverly, and thank you to our audience. Hopefully see you for the next webinar. Bye now.